You've been lied to about JavaScript. You've been told that JavaScript manages memory for you, which is true, but that doesn't mean that you don't need to understand how JavaScript manages that memory. You do need to know. And I see folks making mistakes every day in JS apps because they don't understand how JavaScript works and why it treats arrays, objects, and functions fundamentally different from Booleans, numbers, and strings. Mistakes like putting JSON stringify into a dependency array. Please don't ever do that. If you're doing that, it's because you don't understand how JavaScript manages arrays and objects, and how React and JavaScript detect changes in those objects. So that's what I'm going to teach you in this video. We'll go through the fundamentals of how JavaScript manages memory. It's really genuinely not that hard. But it will teach you the fundamentals so that you understand why arrays, objects, and functions are managed differently from the primitive types, Booleans, numbers, and strings. And then we'll go into change detection and how that works. And finally, we'll cover how to apply it all in React so you understand how it actually works in the real world. So let's start off with some basics. Every programming language that I know of manages memory in two sections, the stack and the heap. And if we think about memory as one big empty array of bytes, the stack is usually at the start of the array, building towards the center. And the heap is at the end of the array, building again towards the center. And if either the stack or the heap get too big and they start overlapping each other, then boom, you get what's called a stack overflow. Yeah, that's where that name comes from. So let's start with the stack because it's actually the one that's pretty straightforward. Say we have a function called main. And we invoke that function. The main function has two local variables, numVal, which is a number, and a flag, which is a Boolean. So where does JavaScript actually store that? Well, because they're local to the function, they're stored in what's called a stack frame. The frame holds any local variables, as well as any arguments to the function, and the return value. Now let's say that main calls another function. Now, as we walk through how this executes, we start off with the stack frame for main. Then we create a new stack frame for another function with the value of numVal copied in there, as well as the space for v, which is the local value. And then we push that stack frame onto the stack. Then in the code, we set v, we console log, we multiply it, we log it again, and then we pop the stack frame off of the stack as we return back into main. So now that you know what the stack is, some things should start to become clear. Like a stack trace shows you the list of where you are in the function and all the stack of calls that happened to have you end up there. And when you look in the browser, you can actually see that firsthand in the dev tools. You can see each call and what the locals are at each frame in the stack. All starts to make sense. And you can also start to see why senior engineers are not so keen on recursion because each iteration of recursion pushes a new stack frame. And if that spins out of control, then boom, stack overflow. Back to the point, though, let's make this a bit more distinct by talking about arrays, because so far we've been talking about numbers and Booleans, and they're easy. They're primitive values, and they're stored, if they're locals like this, in the stack frame because they're a fixed size. But arrays can be huge, right? So storing the whole array in the stack frame doesn't make a lot of sense. Plus, stack frames don't change size, and you change the size of an array if you push or pop or any mutation to it. So you can't really do the stack frame thing with an array. So we store arrays in the heap. Let's change around the code a little bit. Now I've got numVal again, but we've also got an array called numbers with some numbers in it. And so we store those in a block of memory way out at the end of the heap. But how do we know where that is? We've got to create a connection between the numbers variable in the stack frame and the array data that's out there in the heap. So that's when we use a reference. So in the stack frame, in that numbers slot, we have a reference to that array. And that reference is just a location in memory of that array. So let's do another example to learn a little bit more about the heap. Now we've added a position. It's an object this time, but it's the same idea. We put it in the heap, and then there's a reference to it in the stack frame with pause. All right, let's try another one. Now we've got an array inside of an object. Now we've got this object, values, and we've got a reference to that we store in the variable values. But inside of that object, in the heap, we have more references to arrays. that are also stored in the heap. So variables in the stack frame can reference objects and arrays in the heap, and then those objects and arrays in the heap can in turn reference other objects and arrays also in the heap. Now, one more really important thing to know about the relationship between the stack and the heap is how arrays and objects are passed to functions when you call them. Remember back when we had another function and we called it with a number? We just copied that number into the stack frame when we called another function. We did that because numbers are primitive values, and we pass primitive values by value. Now let's change it around. Let's say that we have values again, that object that has other arrays attached to it, and we want to pass that to another function. Well, in that case, we don't copy the structures and then pass the copies. We just send a reference to the data. It's kind of like the difference between a phone and a phone number. I don't have my friend's physical phone, but I do have their phone number, which is a reference to their phone. And if I give it to you, then you have their phone number, not a copy of their physical phone, right? We both have references to their phone. So in JavaScript world, the alternative to passing objects and arrays and functions by reference is just crazy. We'd have to copy all the data anytime you made a call, and that would take up a ton of time and a huge amount of memory. So we just pass references instead. Now, when another function is done, that reference goes away. And when main is done, that reference goes away too, at which point there are no more references to data, and it can be removed by the garbage collector. All right, now we know the fundamentals of how JavaScript manages its memory, although honestly, I have simplified it a little bit because the contents of strings are also stored in the heap, but JavaScript still treats them like they're primitive values when you're comparing two strings. So conceptually, you should probably just treat them as if they're primitive values, like numbers and Booleans, even though they're actually, in reality, stored in the heap. So why do we learn all that? Why does it matter to, say, a React developer to know any of that? Well, it's important for two reasons. First, we now know why JavaScript treats primitive values like numbers and Booleans and strings differently from arrays, objects, and functions. And secondly, it's really important because React's primary job is to convert state into DOM. And whenever that state changes, it needs to re-render the components to update the DOM, which means that we need some indicator to understand when state changes. For primitive values like numbers, it's really easy to detect that. You just compare the old value to the new value, and if they're different, then it's changed. And if they're the same, then no need to update, right? But what about objects and arrays? You'd think, because we look at the contents of numbers and strings, that React would also look at the contents of the old array and, say, a new array to see if there were differences. And if there were, then we render, and if it's not, then it wouldn't re-render. But that's not actually how it happens. So we're going to move on from the stack and the heap stuff and talk about how JavaScript compares different types of data. Strings, numbers, Booleans, objects, arrays, because it's fundamental to understanding how React works. All right, let's start off with a question. If you have two arrays and they both have the same numbers in them and you use triple equals on them, what do you think the result will be? It's going to be false, because when it comes to arrays and objects, we compare them by reference and not by content. That's really important, by the way. That right there. That's why I'm actually making this video. If you come away with one thing, know this. In JavaScript, arrays, objects, and functions are compared by reference and not by their contents. So if you're pounding your head into the wall saying these two data objects are the same, why is useEffect firing? It's because React compares arrays and objects by their memory reference. And even though they have the same contents, they probably don't have the same reference. Now, to be precise, React actually uses object.is for that comparison. It's still false, though, because object.is or triple equals are pretty much identical except for some edge cases. So let's get into object.is because you really have to know this one cold. But honestly, thankfully, it's pretty easy. Let's start with Booleans. How about comparing false with false using object.is? That's true because false equals false. Okay, how about true and false? Well, that's false because true is not false. Pretty easy so far. So let's talk about numbers. 10 is not 20, so that's a big false, but 20 is 20, so true. So Booleans are compared by value, numbers are compared by value. How about strings? So the string hello has the same value as the other string hello, so true, even though in memory they're probably not in the same spot, but JavaScript treats them the same. It's doing a little funny business there because it's just a little bit easier for us as a language to treat strings by value. So JavaScript is just being really nice to us. All right, so far so good. How about two empty arrays? Surely those are the same, right? Nope, they're false because those are really two different arrays in the heap, two different locations, two different references, and therefore it's false. How about this one? Again, false. Good, I'm glad you're paying attention. Again, you have two different arrays with different memory locations, even though they have the same contents. All right, let's switch it up a bit. We'll create two constant variables and try again. But again, false because A and B are in different locations in memory. But if I set B to A, then that's actually true because both B and A are referencing the same array in memory. All right, how about this one? Now we're comparing the first value in the A and B arrays. What do you think? Well, this one is true because the values at those indices are numbers, and they are both 10 and 10 equals 10, so true. So even though we're referencing two different 10s in memory, the numbers is actually what we're comparing, so object.is will be true. All right, let's take a checkpoint here. We've talked about the stack and the heap and how JavaScript stores different types of values. We talked about how to compare primitives versus objects and arrays. So let's put this into practice by taking a look at some real React examples. And we'll start off with everybody's favorite counter component. We've got some count state. It's a number. Got a button. When you click on the button, it'll increment that value by 1. Now, a question for you. If I added a use effect in here, and it's got no dependencies in the dependency array, how often will it fire? All right, only once on the component mount, and that's because it doesn't depend on count. So let's add that. Let's add count. Now how often does it fire? Every time I press the button, right? Cool. All right, awesome. But actually, why? Well, okay, so what's happening here is that React is comparing each value in the new dependency array versus its old value in the old dependency array using our old friend object.is. So that's the reason why we were learning all about object.is. Anyway, if any item in that dependency array returns false from object.is comparing the old value and the new value, then the effect or layout effect or callback creation or memoization happens depending on which hook you use. So say we are currently at 10 and we click on that button, then it'll be 10 for the old value and 11 for the new value, and object.is 10 versus 11 returns false. And so that triggers the effect. But what if we change on increment and just always send back the same value? What fire then? Well, no, but it's not because of dependency arrays. Actually, because the state setting function, setCount, also does an object.is check to make sure that you're not just giving it an unnecessary update. So it says if the new value you're giving me is the same as the old value I had using object.is, then I just shortcut. I'm not going to do anything. It's a nice little shortcut that React has built into it. Now, as we know, primitive values are easy. So let's start talking about objects. So instead of count, we have some data, which is an object, and that data has inside of it the count. And our increment function just updates the count in the data object directly. Should work, right? Well, it doesn't because React has no way of knowing that you made that change. It's not observing that data. So maybe we just need to tell React that the data has changed by calling setData. Will that work? No, because setData is going to use that object.is on the old value versus the new value. So we have the old reference to the data and the incoming value, which is the exact same reference. And it'll say those two things are the same. So object.is will return true, and it'll just ignore it. So what can we do? Well, we can create a new object. Does this work? Yes, it does. Awesome. Why? Because we're creating a new object in the heap with a new reference and then sending it to setData. setData looks at the old object reference versus the new object reference using object.is. It sees they're different. Object.is returns false, and then it sets the state to that new object and requests a re-render. And the use effect also fires for exactly the same reason. React compares the old reference to the data to the new reference to the data using object.is. that returns false because they're different, and the effect is scheduled then to be run. So if you're using React to store data in objects or arrays, you indicate to React that a data has changed by what means. You create a new object or array in memory. So anytime an array or object change, you must create a new object to indicate that change. That's why we see a lot of code that looks like this. We're making a new object with the old data, but with some updates. And you see the same kind of thing with arrays. Here we're creating a new array in the heap with a new reference, cloning the old array, and then we're setting the value and setting the data. Or if you want, you can even get tricky and use something like the new toSpliced. The underlying principle here is immutability. You never change arrays or objects in place. You create a new object or array to replace the old one. And the fact that there's a new object or array reference is the indicator to the framework, React, that the value has changed. So you use toSplice to create a new array with that mutation versus a destructive in-place method like splice. Another example is sort. Sort sorts the data in place by just rearranging the array in the heap while keeping the reference the same. And here's the problem with that. Let's say that we have a function calling another function. Now we start off with a list of names in main with the contents DBA, and we console log those out. Then we call another function with the names. That function calls it data. And notice in the stack frame now that both main and another function are using the same reference. They're both working with the exact same array, not a copy. Another function then sorts the array in place. So now the array has ABD. Uh-oh. So we console log that out, and then we return back to the main function that then console logs out ABD. Now, it's still expecting this to have the same values, but it doesn't because they've been sorted in place. So that's not great. To get around this, another function could use toSorted instead of sorted to sort the array into a new array, but keep the old array the same. Or we can use a copy pattern like we saw with objects, but this time we just create a new array from an old array, and then we do the sort on that instead. Or you can even go even shorter by using the new toSorted. Now, one of the things that I've found folks doing when they don't understand all this reference and immutability stuff is to coerce objects and arrays back into primitive values as strings. Because strings, again, compare by value. For example, you might see something like this, where we use JSON stringify to turn data into a string so that we're no longer comparing by reference, but by the content of the data. Clever, right? No, not at all. First off, this eats memory because this data could be huge, and this makes huge strings that we have to store and compare, which is an ON operation. It's just bad. Secondly, it's slow. JSON stringify is really slow. Way slower than just comparing two memory addresses, which are just two numbers, super easy to compare. So don't do this. Don't do the JSON stringify thing. Do the right thing. Use the references as indicators to react to the contents of the array or object have changed by creating new references. That's the right thing to do. Actually, the rightest thing to do in this case is depend on the count inside of the data, because that's actually all we care about. And if the data is an object, maybe undefined or something, you can even use like optional chaining to even make it safer. All right, we've covered a lot here. I hope this helps you understand a lot more about JavaScript memory management. But what I want you to take away from this are 3 key points. First, in JavaScript, arrays and objects are stored differently from Booleans, numbers, and strings. Second, objects and arrays are managed by reference as opposed to by value. And we learned all about that because we learned the mechanics of the stack and the heap and how and why we store primitive numbers differently than we do arrays and objects. And third, React compares everything using object.is. And that means objects and arrays are compared by reference and not by their contents, which means that React will only know if an object or an array has changed if its reference, its location in memory, has changed. By the way, if you're curious about the impact of comparing contents versus comparing references, I've got a video on that as well. Spoiler alert, it's devastating to performance to compare contents. It's realistically not an option. In the meantime, of course, if you have any further questions on this, be sure to hit me up in the comments right down below. In the meantime, if you like the video, hit that like button. If you really like the video, hit the subscribe button and click on that bell and be notified the next time a new Blue Collar Coder comes out.